Hello and welcome to this paper walkthrough video. We are going to be looking at the May June 2024 paper, that's paper 11 for further pure maths 1. I hope you're ready. Let's get into it. Alright, the question here says the cubic equation 2x cubed plus x squared minus px minus 5 equal to 0, where p is a positive constant, has roots alpha, beta, gamma. All right. And on part A, they now say state in terms of P, the value of alpha, beta, beta, gamma, and gamma alpha. Okay. Which apparently is the sum of product of pairs. So we are saying that for this equation that we have been given originally, the sum of its roots, okay, if we say plus minus is must be minus a half. Okay, so minus a half, and the sum of product of pairs is minus p over 2, or minus a half p, and the product of roots, alpha, beta, gamma, is minus of minus 5, so that's just 5 over 2. So when the question is asking for this, which we know is the sum of product of pairs, we can say that it is equal to basically minus a half of p. Okay, that's the sum of product of pairs. We say the coefficient of x divided by the coefficient of x cubed. I'm sure you got that one correctly, right?
Yes.
Okay, then for part B, they say we should find the value of alpha squared beta gamma plus alpha beta squared gamma plus alpha beta gamma squared. All right, so here we can say alpha squared beta gamma plus alpha beta squared gamma plus alpha beta gamma squared is the same as alpha beta gamma of alpha plus beta plus gamma. Okay, so if you expand the brackets here, you should be able to get this. I hope that's what you considered when you did this question.
Yes.
All right. Okay, perfect. All right, so from here, alpha, beta, gamma is the product of roots, which we have to be 5 over 2. That's times the sum of roots, which we said here was minus 5 over, minus a half. So it's times minus a half. So we should get here minus 5 over 4, right?
Yes.
Okay, good. Let's go on to part C. On part C, they say deduce a cubic equation whose roots are alpha, beta, beta gamma, and alpha gamma. All right. So these are the roots of this new cubic equation. And we're going to use the fact that for this new cubic equation, we'll say that it has to be, say, in terms of y. So it has to be y cubed minus the sum of roots of y squared plus the sum of product of pairs of y minus the product of roots equal to 0. So that is like the structure of the new cubic equation we want to form. Right, so we need to find the sum of roots. The sum of roots would be alpha beta plus beta gamma plus alpha gamma. And this, we've already found it on part A. It's actually minus a half of P. All right. So minus a half of P here. The sum of product of pairs should be these two. So that's alpha beta squared gamma plus these two. That's alpha beta gamma squared plus this two. That's alpha squared beta gamma. And we have found that that asked us this thing, that asked for it on part B, and we got it to be minus 5 over 4. So minus 5 over 4 here. Then the product of roots, for the product of roots for this new equation is going to be the product of alpha beta times beta gamma times alpha gamma, which essentially is alpha squared beta squared gamma squared, which is alpha beta gamma all squared, which is, for alpha beta gamma, we have that right here as 5 over 2. So we just want the square of that. So it's 5 over 2 squared, which is 25 over 4. Okay, so the new equation, therefore, will be y cubed minus the sum of roots. So that's minus of a half of p of y squared, and here plus the sum of product of pairs, that's minus 5 over 4 of y, and it's minus the product of roots. So it's minus this, which becomes minus of 25 over 4 equal to 0. Okay. So this is what we have in here, and that's essentially going to be equal to y cubed plus half of py squared minus 5 over 4 of y minus 25 over 4 equal to 0. I think we can simplify this a little bit more. Maybe just multiply all the terms by 4. So everything by 4 here. And we'll get our final most answer as 4y cubed, right? Plus 2py squared minus 5y and minus 25 equal to 0. So this here will be our answer. So that's how we work it out. I hope you understand this, Amira.
Yes, I understand. Because I asked about this question because you know how the roots are like alpha, beta, beta, gamma, whatever.
Yeah,
In my head, it was like y is equal to that. So I did y is equal to x squared, but it was just like this instead.
I see. All right. So yeah, I think this approach should be a much better one. All right. For part D, okay. I'm sure you did part D, did you?
Yes, I did the
Okay, so we've been given that the sum of squares, we know that the sum of squares is equal to the sum of roots squared minus 2 times the sum of product of pairs. So the sum of squares has been given to be a third, and the sum of squares, sum of roots squared, the sum of roots is minus a half, so a square of that. So minus a half squared minus 2 times the sum of product of pairs must be minus a half p. So minus a half of p. So that's a third is equal to a quarter. And here it's plus p. So p is a third minus a quarter. And what is a third minus a quarter?
Is it 1/12?
1 over 12. So that happens to be the answer. Yeah. So that's how we answer this particular question. Let's move on to the next one. So on question number 2, it says, prove by mathematical induction that 6 to the 4n plus 38 to the n minus 2 is divisible by 74 for all positive integers n. Alright, so we're going to start with proving for n equals to 1. And when n is 1, we'll be having 6 to the 4 of 1 plus 38 to the 1 minus 2, which is, for 6 to the power of 4, we have 1,296, and that's plus 38 minus 2, and this will give us 1,332, so 1332 here. Alright, so this thing that we got, is actually divisible by 74. Okay, 74 goes in 18 times, so it's like 18 of 74. Therefore, it's divisible by 74, and thus n equals to 1 is true. Next, we're going to assume true for n equals to k. So we'll be having 6 to the 4k plus 38 to the k minus 2. And since we are saying that this statement is true, it means that what we have here is divisible by 74. So I'll say it's equal to 74L. Next, we're going to prove for n is equal to k plus 1. So we'll be having 6 to the 4 of k plus 1 plus 38 to the k plus 1 minus 2. So that's 6 to the 4k of 6 to the 4 plus 38 to the k of 38 to the 1 minus 2. Now 6 to the power 4 is 1296. So we have 1296 of 6 to the 4k plus 38 of 38 to the k minus 2. Alright, so we carry on here. I'm going to split this to 1296, actually 1295 plus 1 of 6 to the 4k plus, for 38, that's 37, plus 1 of 38 to the k minus 2. And this will give us 1295 of 6 to the 4k plus 6 to the 4k plus 37 of 38 to the k plus 38 to the k minus 2. So we can rearrange this to 1295 of 6 to the 4k plus 37 of 38 to the k, and for these that will be 6 to the 4k plus 38 to the k minus 2, which is equal to what we have in the assumption. So this whole thing is equal to 74L. Alright. Now, what I'm going to do from here is, for these two, I'm going to factor out 37. And if I factor out 37, we'll be having 35 of 6 to the 4k, and that's going to be plus 38 to the k, and that's going to be plus this, which we said is 74L. Now, looking at this part here, you can see that this term here and this term here are both even terms. Okay, considering that 6 to the 4k is an even term, and 38 to the k is also an even term, and even terms are divisible by 2. So essentially, it's like we have 37 of a multiple of 2, and a multiple of 2, I'm going to call it 2 of something, of 2m. Okay, so let me put it this way. I'm going to say, since 35 times 6 to the power 4k plus 38 to the power k are multiples of 2, therefore I'm going to say they are equal to 2m. Therefore we'll be having 37 of 2m plus 74L basically. So that means we have 74m plus 74L, which is 74 of m plus L. Okay, so therefore it makes them divisible by 74, And so n is equal to k plus 1 is true. So that's how we can prove it. Okay, so from here we're going to say, put in the conclusion to say if the statement is true for n is equal to k, then it is also going to be true for n is equal to k plus 1 as proved, and therefore by the principle of mathematical induction it has to be true for every positive integer n. So that's how we do it for this particular question. Let's move on to question number 3. On number 3, it says use the standard results from the list of formulae MF19 to show that the sum to n of r plus 1 of 3r plus 4 is equal to a 12th of n plus 1 of n plus 2 of 9n plus 19. Alright, so let's work on this problem here. We're going to say here, for the sum from r is equal to 1 up to n of r plus 1 of 3r plus 4, it is the same as the sum from r is equal to 1 up to n of r of, then we expand brackets here, which would give us 3r squared plus 7r plus 4, okay, which would be the sum from r is equal to 1 up to n of 3, okay, 3r cubed plus 7r squared plus 4r. So this is what we are having here. So it's going to be 3 times the sum to n of terms of the form r squared, actually r cubed, plus 7 of the sum from r is equal to 1 to big N of terms of the form r squared, plus 4 of the sum to n of terms of the form r. Now, for sum of terms of the form r cubed, we have it from MF19 as being a quarter, in this case of n squared of n plus 1 squared, and that's plus 7 of the sum of squares is actually a sixth of n plus 1 of 2n plus 1, and that's plus 4 of half n of n plus 1. Alright, so we have here 3/4 of n squared of n plus 1 squared plus 7 over 6 of n plus 1 of 2n plus 1 plus 2n of n plus 1. Alright, now we're going to factor out, okay, from all of these terms, we are going to factor out, let's factor out a 12th of n plus 1. Okay, let's do that. Which means here it's like if we multiply by 12, 4 goes in 3 times, so that's 9. So here we're left with 9 of n plus 1. Here by 12, that's 2. So we have here plus 14 of 2n plus 1. And that's going to be plus here 24. Okay, so this is what we are having right here. So let's carry on. From here we're going to say a 12th of n plus 1 of, now simplifying, for the square terms we have this, okay, that's 9n squared. For the terms in n, we have 9n plus 28n. Now 9 plus 28 is 37, so it's plus 37n. And for the constants, we have 14 plus 24, which is 38. So we have a 12th of n plus 1. And now we're going to have here 9n and n. And for the factors of 38, we can use 19 and 2. Alright, so I'm going to put 19 here and 2 here to factorize. And what we have now is what they want us to have right on here. So I'll say shown. Let's move on. Part B says, express 3r plus 4 over r of r plus 1 in partial fractions, and hence use the method of differences to find the sum to n of 3r plus 4 over r of r plus 1 of a quarter to the r plus 1 in terms of big N. Alright. So in this particular case, we have 3r plus 4 over r of r plus 1 being equal to, in partial fractions, a over r plus b over r plus 1. So multiplying both sides by this denominator, all the terms, we'll be left with 3r plus 4 being identical to a of r plus 1 plus b of r. So from here, I'm going to say, okay, let me take this right on to here. So this has led us to having this. So I'll say let r be equal to minus 1, so that if r is minus 1 here, 3 of minus 1 plus 4 is 1, and it's equal to, this becomes 0, and we have minus b, so b is equal to minus 1. And let r be equal to 0, so that we'll be having 4 is equal to, this part becomes 0, but here we have a of 1, so a is 4 basically. So therefore, we are saying that 3r plus 4 over r of r plus 1 is equal to a, which is 4, over r, plus b, which is minus 1. So that's going to be minus of 1 over r plus 1. So we can now do the method of differences. Alright, the question says we should work this out. So for the sum, that's the sum to n from r is equal to 1 up to n, okay, of 3r plus 4 over r of r plus 1 of a quarter to the r plus 1. I'm going to say this is equal to the sum from r is equal to 1 up to n of, and for this I'll use the partialized form so that we can employ the method of differences. So essentially we'll be having 4 over r minus 1 over r plus 1. Alright, and that's of a quarter to the r plus 1. So I have a quarter to the r plus 1. Now what I'm going to do is I'm going to factor out a quarter, okay, from here. So a quarter outside, and we have from r is equal to 1 up to n. And I'll have this, which is a quarter to the power of r of 4 over r minus 1 over r plus 1. Okay, so I'm going to now employ the method of differences. So I'm going to say this is equal to a quarter of, now when r is equal to 1, we'll be having a quarter of 4 over 1 minus 1 over 2. Alright, close bracket, and that's going to be plus, when r is equal to 2, that's 1 over 4 squared of 4 over 2 minus 1 over 3, and that's going to be plus, when r is equal to 3, 1 over 4 cubed of 4 over 3 minus 1 over 4. Alright, so it goes on and on and on until the very last term, which will be a quarter, it's 1 over 4 to the power n of 4 over n minus 1 over n plus 1, like this. So this is what we have. So this is going to be a quarter of, now expanding brackets, here we'll be having 1, and that's 1 minus an eighth, and that's going to be plus, multiplying into the bracket here, we get an eighth minus 1 over 48. Next we go to here, we get 1 over 48, and for this, that's going to be minus 1 over 256. So it goes on and on and on and on until we come here, which is 1, actually this is like 4 to the power minus n, so it's 4 to the power of 1 minus n, and that's O over n, and that's gonna be multiplying this 2, that's gonna be minus 1 over 4 to the n of n plus 1. Alright, so I think you can see here that these terms in the middle add up all the way, so that should also mean that this one will get eliminated. So the only ones remaining, what will be remaining here is therefore, or let me put it this way, therefore what we're looking for, which is the sum to n of 3r plus 4 over r of r plus 1 of a quarter to the r plus 1, alright, should be equal to a quarter of 1 minus 1 over 4 to the n of n plus 1. So essentially this, and this can be simplified to a quarter minus 1 over 4 to the n plus 1 of n plus 1. So this here is the answer. So that's how we do it for part B. Let's move on to the last part, that's part C, where they say we should deduce the value of the sum to infinity of this. Alright, so this is going to be equal to the limit as n approaches infinity of a quarter minus 1 over 4 to the n plus 1 of n plus 1. Alright, so for the constant, we just have a quarter, and on this part, as n approaches infinity, we can say that this whole thing will tend towards 0, okay, because the numerator is constant and the denominator keeps on increasing, so this will tend towards 0. So we'll just be left with a quarter for the answer. So that's how we do it right here for part C. Let's move on. On question number 4, it says the matrix M is given by M is equal to half minus half root 3, half root 3 and a half, pre-multiplying 14, 0 and 0, 1. So in part A, the matrix M represents a sequence of 2 geometrical transformations in the xy plane. Give full details of each transformation and make clear the order in which they are applied. Alright. Okay, so in this case, we have a sequence of 2 transformations, and the order, we start with the second one. That's going to be the first transformation, and the first one is going to be the second transformation. All right, so we're going to start with 14, 0, 0, 1, which essentially would mean if we have a point 1, 0, the point 1, 0 is being transformed onto the point, this point, 14, 0. So 1, 0 to 14, 0. So it's moving to the right. And the point 0, 1 is being transformed onto the same 0, 1. So we can see here that this transformation is essentially a stretch. If we had an original diagram, an original shape say a unit square, is being stretched in a one-way stretch, okay, in the x direction. So I'm going to say that it's a one-way stretch. That's transformation number one. One-way stretch parallel to x-axis with the y-axis invariant and with a factor of 14. So that's the first transformation. Then we're going to do for the transformation represented by the other matrix, a half minus a half root 3, a half root 3, and a half. So essentially, if we have, say, the axis like this, right, and we have starting with the 0.10, so the 0.10 is being transformed onto this, onto a half and half root 3. Okay, let me put it this way, a half and half root 3. Okay, so a half and half root 3 could be somewhere here, okay, with this being a half and this being a half root 3. So this point here, so essentially I can see that it's some kind of a rotation. It's actually a rotation anti-clockwise with an angle. Let me call that alpha, where alpha is actually arctan of half root 3 over a half, arctan of root 3, which is a third pi. So the second transformation, I'll say, is a rotation, okay, and that is the center origin, and it's a third pi anti-clockwise. So that's the second transformation. Okay, so those are the two transformations going on, and that's the order. Let's go on to part B. They say write M inverse as the product of two matrices, neither of which is I. All right. They want us to write down M inverse as the product of two matrices. But we know that M inverse is the product of, the matrix M itself is a product of two matrices. Okay. So we're going to use the fact that, if you have two matrices, A, B in a product, their inverse is equal to the inverse of B, pre-multiplying the inverse of A. So this is an important rule. So that's the one we're going to use. So M inverse is as good as the inverse of the second matrix, which is the matrix 14, 0, 0, 1. And the inverse of that matrix, the determinant of that matrix is 14. So it's 1 over 14 of, and we switch the positions of 14 and 1. So 1 and 14, then 0, 0. So this is the inverse of the second matrix. Pre-multiplying the inverse of the first matrix. The determinant of the first matrix is essentially, if we say a half times a half, that's a quarter minus the product of these two, it will become a plus. That's a quarter, that's actually 3/4. So it's essentially 1, that's the determinant. And we switch positions of a half and a half and change both the signs of minus a half root 3 and half root 3. So the inverse is essentially a half, then half root 3 and minus a half root 3. So this is what we have in here, and that's actually what they want. Okay, they had said as a product of two matrices, neither of which is I can multiply 1 over 14 into the bracket, so we can have M inverse being 1 over 14, 0, 0, then 1, of a half root 3 minus a half root 3 and a half. So this is the answer to part B. Let's move on to part C. They say find the equations of the invariant lines through the origin of the transformation represented by M. Okay, So M is the product of the two matrices, and the matrices are a half minus a half root 3, a half root 3, then we have a half here. Then the second matrix is the matrix 14 0 0 1. So we have 14 0 0 1. So this is going to give us, multiplying row column, that's going to be half of 14, that's 7, and that times 0, that's 0, so 7 here. Then row and outer column will give us minus a half root 3. Then row and column will give us 7 root 3. Then row and this outer column will give us a half. So this is what we have for the matrix M. So we want to look for the invariant lines through the origin, which means if we multiply the matrix M, that's 7 minus a half root 3, 7 root 3 and a half times xy, we get the image big X and big Y. That's the image. So that's basically 7x minus a half root 3 of y equals to big X. Then 7 root 3 of x plus half y is equal to big Y. Now, since we are saying that the lines pass through the origin is given, it means that y should be equal to mx. So therefore, where there's y, we're going to put mx in the equations above. So we'll be having 7x minus a half of root 3 mx is equal to big X, and 7 root 3 of x plus half of mx is equal to big Y. So next, we're going to appreciate also the fact that the lines are invariant. So I'll say also, since the lines are invariant, it means that the image will also take the form y is equal to mx, which therefore means for y, which is 7 root 3 of x plus half mx should be equal to m of x, 7x minus half root 3 of mx. Right, now all the terms are divisible by x, so we're going to divide all of the both sides by x, so that we have 7 root 3 plus half m is equal to, expanding the brackets, 7m minus half root 3 m squared. So we're going to rearrange. So we have half root 3 of m squared, and half minus 7, that's minus 13 over 2, so we have minus 13 over 2 of m, and that's going to be plus 7 root 3 should be equal to 0. Okay, I'm going to multiply both sides by 2, so we have root 3 m squared minus 13m plus 14 root 3 equal to 0. Alright, so for these equations, we're going to solve them, maybe making use of the quadratic formula. So m is equal to minus b plus or minus the square root of b squared minus 4a c, alright, and that's divided by 2a. So that's 13 plus or minus the square root of, and for what's inside the bracket, 13 squared is 169, and it's going to be minus 4 times root 13 times 14 root 13 is like 4 times 14 times 3, and that's 168, and that's all over 2 root 3, which will give us, okay, let me make use of the space here. So I'm going to place this here. So I'll move this up a little, just one line upwards like this. All right, so what we have is 13 plus or minus the square root of 1 essentially. All right, so it's plus or minus 1 over 2 root 3. I'm just going to multiply, to rationalize the denominator. I'll multiply by root 3 over root 3. So we essentially have 13 plus or minus 1 of root 3 all over 2 of 3, which is 6. All right, simplifying this. So therefore, the possible values of m will be 13 minus 1, which is 12, and 12 root 3 over 6 is 2 root 3. Then 13 plus 1, that's 14, and 14 root 3 over 6 is like 7 over 3 root 3. Okay, so the invariant lines will be y is equal to 2 root 3 of x and y is equal to 7 over 3 root 3 of x. So these are the answers. Okay, let's move on to part D. On part D, the question says, the triangle ABC in the xy plane is transformed by M onto triangle DEF. Given that the area of triangle DEF is 28 square centimeters, find the area of triangle ABC. Alright, so we have triangle ABC and triangle DEF, and by matrix M, we have this mapping. Alright, and we've been told that the area of triangle DEF is 28 square centimeters. So they want us to find the area of triangle ABC. So we know that the area of triangle ABC, okay, times the determinant of M should give us the area of the image of triangle DEF. So to get the area we want, okay, the area of triangle ABC, it has to be the area of triangle DEF, 28, over the determinant of M. Now the determinant of M, remember M, we got it to be equivalent to this. Okay, so let me copy it and paste it down here. So this is the matrix M. Now the determinant of M is 7 over 2, and that's minus the product here, which is going to be 7 over 2 minus 7 over 2 of root 3 times root 3 is 3, basically. So it's like we're saying 7 over 2 plus 21 over 2, which essentially is 28 over 2, so that's 14. All right, so that's the determinant of M. So that's 14, which leaves us the area of triangle ABC to be 2, and that's square centimeters. So that's the answer right here. All right, so that's how we do it for this question. Let's move on to number 5. On number 5, the question says, the points A, B, C have position vectors 2i plus 2j plus 4k of 2i plus 4j minus k and minus 3i minus 3j plus 4k respectively, relative to the origin OR. So on part A, find the equation of the plane ABC, giving your answer in the form ax plus by plus cz equal to d. Alright, so we have here a plane, and on this plane we have 3 position vectors. Okay, so we have A, we have B, and we have C, and we want to find the equation of the plane. So we're going to first find vectors, 2 vectors that are on the plane, 2 vector lines that are on the plane, which means we'll need to find AB, and in this case AB is OB minus OA, and OB is 2i plus 4j minus k minus OA, which is 2i plus 2j plus 4k. So essentially 2 minus 2i, that's 0. 4 minus 2, that's 2j. And minus k minus 4k gives us minus 5k. So that's AB here for us. Okay, so we now have AB. Next, we want to find the vector AC. And to find AC, we'll say that's OC minus OA. Now for OC, that's minus 3i minus 3j plus 4k minus OA, which is 2i plus 2j plus 4k. So that's gonna give us minus 5i minus 5j, and 4k minus 4k is 0. So it's just minus 5i minus 5j. Now we want to find the common perpendicular to these two vectors, which is n. So to get n, we will do vector product. That's AB cross AC. So essentially we are going to be having 0, 2, and minus 5 cross multiplying minus 5, minus 5, and 0. So this will give us, if we close out row and column and we do 0 minus 25, that will give us minus 25. So we have minus 25i. Next, I'll close out this and I'll have 0 minus 25 again, but with a minus that we remember we use the matrix of signs, so we put a minus on that, so that's S squared S plus 25j. Then we close out these two and we do 0 minus minus 10, which is 10. So that's plus 10k. So this is what we have in right on here. Alright. Now, with what we have, we're also going to need to find the distance, okay, d, which we know is a dot n. Alright. So this means that d will be equal to a dot n dot product. A is any point on the plane. Let's use the point A, which is 224. So 224 dot these, that's minus 25, 25, 10, which would give us minus 50 plus 50 plus 40. So basically that's 40 right here. So therefore the vector equation will be r dot minus 25, 25, 10 being equal to 40, and we can also have it in Cartesian form. So the Cartesian equation will be, because the question actually says it has to be in Cartesian form, this form here. So in Cartesian form, that's going to be minus 25x plus 25y plus 10z equals to 40. We can reduce this by dividing each one of the terms by 5. Alright, so this by 5, this by 5, this by 5, this by 5, and when we do, we'll be having it as minus 5x plus 5y plus 2z equals to 8. So that's the answer here, and that's how we do it. Let's move on to part B. It says the point D has position vector 2i plus j plus 3k. Find the perpendicular distance from D to the plane ABC. So we have the plane ABC and a point D here, and we want the perpendicular distance. That's what we're looking for. So we're going to make use of the formula. D is equal to under modulus ax1 plus by1 plus cz1 minus d over the square root of a squared plus b squared plus c squared. So this is what we're going to be making use of. So therefore, d will be equal to under modulus, alright. Remember the equation of the plane is what we got right above. That's the ax plus by plus cz equals to d, alright. So I'm going to place it on here because we're going to make use of this. So we're saying that's going to be minus 5 of 2, this 2, plus 5 of 1, plus 2 of z, which is 3, minus 8 over the square root, and that's the square root of minus 5 squared plus 5 squared plus 2 squared. Alright, and we're going to simplify this thing that we have. So that's actually equal to, under modulus, the numerator is minus 10 plus 5 plus 6 minus 8, and that's over the bottom is root of 25 plus 25 plus 4, which is root of 54. So this is coming out to be the modulus of, okay, let me just use the space down below, under modulus, minus 10 plus 5, that's minus 5 plus 6 is 1, and 1 minus 8 is minus 7. So that's minus 7 over root 54. And the answer should therefore be 7 over root 54. So that's the answer we're getting for part B. Let's move on to part C. On part C, they say, find the shortest distance between the lines AB and CD. Alright, so here, we're going to make use of the fact that the shortest distance between two lines can be found by d is equal to the modulus of a1 minus a2 dot b1 cross b2, and that's over mod of b1 cross b2. And this is for when r is equal to a1 plus lambda b1 and the line r is equal to a2 plus mu b2. Now in this case we have two lines. We have the line AB, and for the line AB, the vector line AB, the equation is r is equal to a point on AB. We can take the point A, which is the point 2, 2, 4. So we have 2, 2, 4 here, and that's plus lambda of the direction of AB. Now the direction AB, we got it to be here. That's 0, 2, and minus 5. So 0, 2, and minus 5. We will also need the line CD, which will be r is equal to a point C or D. Let's take the point D here. That's 2, 1, 3. So I have here 2, 1, 3, and that's plus mu of the direction CD. Now for the direction CD, we'll say that CD is OD minus OC. OD is 2, 1, 3, so it's essentially 2, 1, 3 minus OC. C is here. That's minus 3, 4. So we have here minus 3, 4. Alright, so this is going to give us r being equal to 2, 1, 3 plus mu of 5, 4, and minus 1. Alright, so now we want to find a1 minus a2, which we are making use of. This is a1 and this is a2, so that'll give us 2, 2, 4 minus 2, 1, 3, which is equal to 0, 1, 1, like this. And then we are also going to have b1 cross b2. We will say the directions, okay, 0, 2, minus 5, cross multiplying 5, 4, and minus 1. Alright, so this is going to be here, if we close out, we'll have minus 2 minus 20. So that essentially gives us 18. So we have 18 here. Alright, so next, I'll close out here. So that's going to be 0 minus 25, which is 25. So we have 25 here. Sorry, so 25. And it's going to be minus 25 because it's plus minus plus essentially. Then we will close out here. And that's 0 minus 10. So it's minus 10. So this is what we have in right here. So we will also need mod of B1 cross B2, which is the square root of 18 squared plus 25 squared plus 10 squared. So that's going to be equal to the square root of 1049. So we are therefore saying D is equal to here 0, 1, 1, okay, under modulus dot B1, B2, that's 18 minus 25 minus 10, and that's over the square root of 1049. And this will give us D being equal to, here we get minus 25 minus 10, that's minus 35, and that's going to be over the square root of 1049, and this is going to give us 1.08. So 1.08 is the answer right here. And that's how we do it for this particular question. Let's move on to the next one. So the curve C has equation y is equal to x squared plus ax plus 1 over x plus 2, where a is greater than 5 over 2. So on part A, find the equations of the asymptotes of C. All right. We get the vertical asymptote by equating the denominator to 0. So the vertical asymptote is x equals to minus 2. Okay, I hope that's okay.
Yes.
Then for the oblique asymptote, we can divide x plus 2 into the x squared plus ax plus 1. So dividing x squared by x, we get x, and x times this would give us x squared plus 2x, and we subtract. When we do x squared minus x squared is 0, ax minus 2x is a minus 2 of x, and we bring down 1, and we divide this by this x, and we're going to get a minus 2, and we multiply a minus 2 by this, and we will get a minus 2 of x. All right. And that's going to be plus 2a minus 4. All right. So we're going to subtract again, and we will get the remainder as a minus 2 of x minus a minus 2 of x is 0. 1 minus this should give us minus 2a, and that's minus 2a plus 5. All right. So that's what we have. But for the oblique asymptote, we just want the quotient. So therefore, the oblique asymptote is y is equal to x plus a minus 2. Okay, is that what you got for this?
Yes, I got that.
Good, that's fine. Now on part B, they say, show that C has no stationary points. Okay, now we have the original equation. We know that to find stationary points, we will do differentiation. So basically, since we have the equation as y is equal to x squared plus ax plus 1, so x squared plus ax plus 1 over x plus 2, all right, we will find dy by dx, because we know that at the stationary point dy by dx is equal to 0. So we'll differentiate quotients, that's x plus 2 of the derivative with respect to x of x squared plus ax plus 1 minus x squared plus ax plus 1 of the derivative with respect to x of x plus 2. And that's going to be all over x plus 2 squared. And we equate this to 0. Now, we will remain with the numerator because if we multiply both sides by the denominator, it becomes 0 on the other side. So we will be left with x plus 2 here. And differentiating this gives us 2x plus a. All right. Are you following?
Yes.
Okay, good. Then that's going to be minus here x squared plus ax plus 1. And for this derivative, we just get 1. So it's all good. So this is all going to be equal to 0. Now we expand brackets here. And when we do, we'll be having 2x squared plus 4x plus ax plus 2a. And on this part, that's minus x squared minus ax minus 1 equal to 0. That's 2x squared minus x squared is x squared. So we have x squared. And ax minus ax is 0. So we are left with 4x. And the constants, 2a minus 1. So it's going to be plus 2a minus 1 equal to 0. Now, do we have stationary points existing? Okay, because they want us to show that there are no stationary points. So let's test. We're going to do the discriminant. So for b squared minus 4ac, it's going to be, okay, let me do it this way. For what we have, we know that a is 1, b is 4, and c, the constant, is 2a minus 1. So therefore, for b squared minus 4ac, that's 4 squared minus 4 of 1 of 2a minus 1. Okay, which is 16 minus 8a plus 4, which essentially is 20 minus 8a. Okay, so 20 minus 8a is what we are getting. Now, 20 minus 8a, we're considering that the question tells us that a is greater than 5 over 2. So a is greater than 2.5. Okay. And we're saying since a is greater than 2.5 or 5 over 2, if you say 20 minus 8 times 2.5, you get 0. So anything greater than it, okay, you can try anything like 2.6, will always be negative. All right. So since a is greater than 2.5, 20 minus 8a will always be negative. Okay. Therefore, we can conclude that there are no stationary points on the curve C, because if we are having a stationary point, I mean b squared minus 4ac coming out as being negative or less than 0, it means there are no real roots, which means therefore there are no stationary points. Okay, do you understand this reasoning?
Yes, like I did up till the differentiation part by myself, then I
Okay,
didn't like I completely forgot how to like that I needed to do the discriminant. That's why I was stuck.
I see, I see, I see, I see. All right. Anyways, let's move on. So there's a part C here where they say sketch C, stating the coordinates of the point of intersection with the y-axis and labeling the asymptotes. Okay, so I'll draw two axes, the y-axis here and the horizontal axis here. I will put in the asymptotes. X is equal to -2 is the first one. So I'll draw it here, the asymptote. This is the vertical asymptote intercepting at -2 here. And we'll also have the oblique asymptote. The oblique asymptote is y is equal to x plus a minus 2. A is 2.5. I mean, it's greater than 2.5. Okay. So the y-intercept, 2.5 minus 2 is 0.5. So it has to be greater than 0.5. So basically, the intercept is positive. Okay, so the line will, remember, we're drawing the line y is equal to x plus a minus 2, right? X plus a minus 2. When x is 0, y is a minus 2. A minus 2 is anything greater than 0.5. Okay, so we just draw the line like this. And when y is 0, x will be 2 minus a. All right. Remember, a is anything greater than 2.5. So 2 minus anything greater than 2.5 should be something, it should always be less than minus 2. So it should be coming from a point like this, the one that we have. Okay. So I think we have drawn the line quite well. I'm going to do this. Okay. And we'll have the line being, all right. Now we know that we have an oblique asymptote here, and we've also established on part B that there are no stationary points on C. So this is a type of graph. Since there are no stationary points, you know that it can either be a type of graph like this one, but this type here, will have stationary points, so that's not really the one. So it has to be this type of graph that we supposed to sketch. All right. And it should come like this. We have to understand where the graph intercepts the y-axis and the axis. Okay, we also need to be cautious of that. So let's really take a bit of care with that. For this original graph, okay, let me just copy it. Paste the equation here. All right. For the curve, for where it crosses the x-axis, okay, let me just say when x is 0. When x is 0, y will be equal to a half. So it intercepts the y-axis at a half. Okay. So we know that it intercepts here. So I've properly drawn it. So I think that actually helps. Okay. So this is actually how the graph is going to be. And the question had said we should also state the coordinates of the point of intersection with the y-axis. And we said it intersects the y-axis at a half on the y-axis. So the coordinates are 0 and a half. So that's how we do it. I don't know if you did the curve the same way.
I did the curve the same way. Yeah.
Okay, that's good. Now on part D, that's D part 1, they say sketch the curve, which is essentially the modulus of the curve above. I'm going to do it this way. Okay, so this is the graph we had right above, and I'm going to reflect the part of the graph that is below the x-axis, all right, in the y-axis. So this line segment will come out like this. It's not a straight line, it's a curve, so I think if we do it this way, it should be good. So we've reflected this line segment. So I'm now going to erase it. Okay, so it's no longer here. All right, something like this. And this other line segment, we reflect it in the x-axis. Let me use so it will be like this. So let me erase it from down below. Okay. So this is what I'm getting right on here. All right, that's the type of graph I am getting. Did you get a similar graph for the modulus graph?
Yes, I got the similar one.
Okay, good. So yeah, just increase the size a little. Okay, let's move on to the next, okay, on part 2 here, they say on your sketch in part 1, draw the line y is equal to a. Draw the line y is equal to a. All right. A is greater than 2.5. So it can be a line like this, a horizontal line. So this here is the line y is equal to A. That's the line y is equal to A that I've just drawn on the graph. Now, on part 3, they now say it is given that mod of the function is less than A for these values and those values. Find the value of A. All right. Okay. All right. So quite an interesting question it is. For mod of x squared plus ax plus 1 over x plus 2 being less than A. All right. We are going to, it's a modulus inequality. So we're going to have for its solutions, x squared, we're going to consider x squared plus ax plus 1 over x plus 2 is equal to plus or minus A. So essentially, we're going to say it is going to be equal to minus A, and it is going to be plus ax plus 1 over x plus 2 is equal to positive A. All right. So this is essentially what we have. So what this really means, okay, or maybe another way to look at this would be to say, if you look at the line segments we have, the line segments which I'm highlighting in red are the ones that were reflected. Okay. These are the reflected line segments, and the one that I've kept in black are the ones from the original. So the ones from the original are the ones from the equation, okay, the ones represented by the bold line, bold black line, are the ones for y is equal to x squared. Okay, let me write that down. Y is equal to x squared plus ax plus 1 over x plus 2. And the ones in red, okay, the ones I've just are the ones for are reflected. So they are minus of x squared plus ax plus 1 over x plus 2. So that those are the two line segments we got. But they are intersecting with the line y is equal to A, right? So we want the points of intersection with the bold, the black line, which are this point, and this point. And we find this by saying x squared plus ax plus 1 over x plus 2 is equal to, it intersects with y is equal to A, so it's equal to A. So that's what's equivalent to this equation. All right. And where the line y is equal to A intersects with the red line, this one and this one here, is where this, which is minus of x squared plus ax plus 1 over x plus 2 intersects with the line A, which is the same as, we can take the negative sign to the left and we say this is equal to minus A. So this equation is equivalent to this. So basically what we're trying to do is to find those points of intersection. Okay, are you tracking?
Can you repeat the last part about how like which equations mean what? Because you said just the last thing you said.
The last thing you mean do you mean for this equation here? Or
Yeah,
even,
like those two equations and which, like, you know how you connected it with an arrow? Like, can you explain those? Like,
okay, it's fine. It's all right. It's perfectly fine. So the basic thing here, not so complicated. The basic thing here is what we are seeking to do, okay, and we know that that's going to help us to find the value of A as they want. We want to find the points of intersection. Okay, we have 4 points of intersection, right? So for the first two point of intersection, this, I don't know, let's call it alpha and beta. Those are the points of intersection of this curve and the line y is equal to a. So that's why I equated those two. All right.
Okay.
And I was saying this is the same thing I had written here already.
Oh, okay.
Mhm. And the other one, um, other points of intersection are this one here, which we can use, I don't know, a gamma, and this one will be, what are the Greek letter? Sigma
Delta.
or delta, yeah. Delta would be, those two. So that's when this graph intersects the graph y is equal to a. So that's why I equated the two here. And this equation
Oh,
is the same as this one here.
okay, I got you.
Okay, good. Okay. Anyways, let's carry on. So let's see how if we can make sense of what we have. So essentially, because we'll need to economize the space we have because we have little space here. We're going to, multiply both sides by x plus 2 here. So x squared plus 8x plus 1 is equal to minus ax plus minus 2a, right? Minus 2a, which is x squared plus 2ax plus 1 plus 2a equal to 0. Here we get x squared plus ax plus 1 is equal to ax plus 2a. So x squared and ax minus ax is 0. So it's plus 1 minus 2a equals to 0. Okay. So this is what we are having right on here. And this one is easier to work with because we can say x squared is equal to 2a minus 1. So x is equal to plus or minus the square root of 2a minus 1. So for this one, we're good. All right. For the other one here, so we have to do the formula, quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. All right, so that's minus 2a plus or minus the square root of 4a squared minus 8a minus 4. So this is what I am seeing here. O over 2, okay, which is essentially, if we divide everything by 2, we get minus a plus or minus the square root of, and if we factor out 4 on this, square root of 4 is 2. So we are just left with a squared minus 2a minus 1. Okay, so these are the roots we have. So we now have the 4 roots. Okay, all right. Now, according to the question, okay, the solutions we should get, okay, for the inequality. Let me remove this to make sense of this because we're almost done. Okay, but I really want you to understand what's going on. Okay, so to solve this equation here, Amira, it's the modulus graph is less than a. Okay, the modulus graph is less than the graph of y is equal to a. That's how you should view this. The modulus graph is vertically below the graph of y is equal to a. So our solution should be what I'm highlighting in yellow. These parts of the graph are the parts that are satisfying the inequality. Okay, let's just use the letters, even though they're not in any good order. Okay, but I have gamma, alpha, delta, beta. Okay, so the solutions are essentially values of x that are between gamma and alpha. So from gamma to alpha, sorry, that's alpha. from gamma to alpha. And the other set of values satisfying this inequality are from delta to beta. So those are the two solutions. Okay. Let's look at these. Okay. Let's start with the first one, gamma to alpha. Okay, just hoping that I don't complicate things for you, but we're almost there. Okay, so copy. Let's bring it down here. We have little space, so I'm going to create a bit of space here. Okay, so the solutions. The first one is gamma to alpha. Okay, what is gamma and alpha? Gamma is the solution, the red solution, all right? The red solutions are the ones for the reflected. Okay, so the red solutions are the ones where they intersect with the reflected graph. So these are the ones. These are the red solutions. So where the red line, the lower one is minus a, minus, so let me write that down. That's minus a minus the square root of a squared minus 2a minus 1. And it's less than x and it's less than alpha is this point here, the black solution where the original graph intersects. So these are the solutions we got for the black intersection. So then the negative 1 minus, so this is supposed to be minus the square root of 2a minus 1. So these are the first solution. And then the second set of solutions is this one here. That's from gamma to delta to beta. So delta to beta. Delta is this point here, which is reflected, the red intersection, the higher point, which will be minus a plus the square root of a squared minus 2a minus 1 less than x less than beta is the positive one here. That's the square root of 2a minus 1. So these values that we've gotten are comparable to this and this. Okay. The first solution is minus 5 minus root 14 is less than x is less than minus 3. And the other one is less than 3. So we can take any one, okay? We are now saying that, say, for example, if we take this 3, it corresponds to the square root of 2a minus 1. So we can just say 3 is equal to the square root of 2a minus 1, square both sides. So 9 is equal to 2a minus 1. So 10 is equal to 2a. Therefore, a is 5. So this is the answer. That's the value of a. Okay, well, I don't know. It's a bit of a wild question, but I don't know if you understood what I did here.
I understand.
You do. Okay, perfect. Perfect, perfect, perfect. Now we need to move on to the next question, which is question number 7. So on question number 7, it says the curve C has polar equation r squared is equal to pi minus theta of arctan of pi minus theta, and thus for values of theta ranging between 0 and pi. So on part A, sketch C and state the polar coordinates of the point of C furthest from the pole. Alright, so in this particular case, we're going to consider a polar plane, and the range of values is from 0 to pi. So I'm going to have a quarter pi increments so that we have 4 intervals. So we have 0, a quarter pi, half pi, 3/4 pi, up to pi. Now, from the equation that we've been given, we can make r the subject by square rooting both sides so that its r is equal to the square root of pi minus theta of arctan of pi minus theta. So making a table of values with these theta values, And substituting into this equation, we'll be having to one decimal place the values of r being, when theta is 0, r is 2.0. When theta is a quarter pi, r will be 1.7. When theta is a half pi, r will be 1.8. When theta is 3/4 pi, r will be 1.7. And when theta has a value of pi, r will be 0. So we can plot out the points, these points, onto the plane, and they come out like this, and so the curve would come out like this. Alright, so I'm gonna put the sketch here. So this here is the initial line. Okay, so that's theta equal to 0, with the pole being right here. And the curve comes out like this. Now here, the question also says we should state the polar coordinates of the point of C furthest from the pole. So the point furthest from the pole should be this point here, where theta is 0. So r squared will be equal to, that is when theta equal to 0, r squared will be equal to, so we substitute 0 for theta. So we'll be having pi of arctan of pi. So r will be the square root of that, which comes out as, to 3SF, 1.99. Alright, so therefore the coordinates will be 1.99 and theta is 0. So that's the answer right here to part A. Let's move on to part B now. So on part B, they say using the substitution, u is equal to pi minus theta, or otherwise, find the area of the region enclosed by C and the initial line. So let's work this problem out. Okay. We are going to consider, this is substitution, right? So since u is equal to pi minus theta, we know that du by the theta then will be minus 1, and therefore we can substitute the theta with minus du. Okay, if we make the theta the subject. So this is what we have right here. Okay, from the information given, this led to this and this led to this. Anyways, we're also going to consider the limits. Okay, the original limits from the question were 0 to pi. So we are going to say, since values of theta were 0 and pi, how about the values of u? And we're going to make use of the substitution. So when theta is 0, u will be pi. And when theta is pi, u will be 0. So there's kind of like a change. Lower limit becomes upper limit becomes lower limit. Okay. So that's also another very important thing. The formula for area is the integral from alpha to beta of half r squared with respect to theta. So in our case, therefore, the area enclosed will be the integral from 0 to pi. Okay. Let me do it this way. Factor out a half. I'll take out a minus because of the interval change. Remember, this was lower limit and this was upper limit. But when it goes to you, what was the lower limit becomes the upper limit, and what was the upper limit becomes the lower limit. So to take account of that, I put a negative on here. Okay, did you get that?
Yes, I get it.
Then of r squared. Okay, r squared is this. Okay, that's pi minus theta of arctan pi minus theta. pi minus theta of arctan pi minus theta. Okay, but we need to substitute u, sorry. So if we substitute u for pi minus theta, it becomes u of arctan of u. And for d theta, we substitute that with minus du. So we have minus du. Okay. So essentially we have half of the integral from 0 to pi of u arctan of u with respect to u, because the negatives will give us a positive. Okay, I hope you're tracking.
Yes.
All right, good. Now, with this, what we have here, it's actually a product, and we're going to use integration by parts. Okay, we're going to use integration by parts. So, what we're going to do here is, I will say let big U be equal to arctan U and dv by dx. We're just doing this so that we can, integrate. Playing around with the variables can be a bit confusing. It's being equal to u. So du by dx would be differentiating arctan u. If you go to your MF19, you find that we should get 1 over 1 plus u squared in this case. And v here will be half u squared, essentially. All right. So that so this piece of information was just to help us to do integration by parts. So we can now continue. So the area is half of the integral, sorry, half of uv product, which is half u squared arctan of u with the limits, no arrow here, 0 to pi minus the integral, okay, of from 0 to pi of these two, all right? So that's v of du by dx. So essentially, that's gonna be theta outer half here. So let's just make use of space. So that's a half of the integral of u squared of 1 plus u squared with respect to u. So I just multiplied this two. Okay. So that's integration by parts, and I'll put a bigger square bracket right on here. So this is what we have, and let's carry on simplifying. That's half of, okay, I'm not simplifying this part yet, u squared of arctan u, limit 0 to pi minus a half of 0 to pi. We need the limits of the integral from 0 to pi. If you look at u squared plus 1, u squared over 1 plus u squared, we can actually express it in such a way that because we know that it's an improper fraction, it's basically u squared over 1 plus u squared should be equal to u squared over u squared, that's 1, plus a constant over 1 plus u squared. So that's u squared is identical to, multiply both sides by 1 plus u squared, that is 1 plus u squared plus a, just plus a. Okay, so essentially what I did was I multiplied both sides by 1 plus u squared, 1 plus squared by 1 plus u squared, and that's what gave me this. But let's continue. So if we say u is, say, 0, so it will mean that 0 will be, this becomes 0, 1 plus a, therefore a is equal to minus 1. So we can express it in the form 1 plus a over 1 plus u squared as 1 minus 1 over 1 plus u squared with respect to u. Okay, did you get that?
Can you repeat this part?
Okay, it's fine. Let me do that. I think I was a little bit too quick with it. Okay, so let me do that quickly. All right. I think I can use the space on the right side. So what I essentially did was I'm just trying to, because we want to integrate u squared plus 1, or u squared over 1 plus u squared. So what I was trying to say was um, u squared over 1 plus u squared, we can partialize it to 1 plus a constant over 1 plus u squared. Okay, are you okay with that part?
Okay.
All right. So I multiplied both sides by 1 plus u squared, all the terms by 1 plus u squared, this one plus 1 plus u squared, and they cancel here. We're left with u squared equals to 1 plus u squared, and here they cancel, so it's plus a. And I'll say let u be equal to, say, 0. So therefore, on the left side, we'll be having 0 squared is equal to 1 plus 0 squared, which is 1 plus a. So the value of a is minus 1. Therefore, u squared over 1 plus u squared can be written as 1 plus minus 1 over 1 plus u squared, which is the same as this.
Okay.
Okay, I hope you got that now.
Yes.
Okay, good. Nice. So let's carry on. So now we are saying a half of, and now let's do the substitutions. It'll be half of pi squared of arctan of pi. But if we substitute 0 for u, we get 0. And it's going to be minus. Now we go to this part, a half, or maybe let's close bracket. And when this half multiplies this, it becomes a quarter. All right. So we have here a quarter of integrating 1 with respect to u gives us u. And here, integrating 1 over 1 plus u squared gives us arctan of u. This, and that's 0 to pi. Okay. And look at the little space they've given us. But anyways, let's continue. So that gives us here, expand the brackets, a quarter. Okay, it's actually one thing, a quarter pi squared arctan of pi minus a quarter of, substituting pi, that's pi minus arctan pi. So we have a quarter pi squared arctan pi minus a quarter pi plus a quarter arctan pi. These two, we can factor out arctan pi, or a quarter of arctan pi. Or maybe we can just type this whole thing into the calculator to get our answer. Because do they say it has to be exact? Do they? No. Okay, let's just type this in. Let me do that quickly. Just changing to radians. And in radians, I'm getting 2.6456 to 3SF is 2.65. So this here will be the answer to this question here.
Okay.
I hope you got that. You followed through the working.
Yes, I did.
Okay. What can you say about this type of question?
I just actually just need to work on my integration. Like every time I do it, there's like one mistake or two mistakes that I make.
You see, a little bit more practice will certainly help indeed. Yes. All right. So part C says, show that at the point of C furthest from the initial line, 2 of pi minus theta of arctan of pi minus theta of cot theta minus of pi minus theta over 1 plus pi minus theta squared minus arctan of pi minus theta is equal to 0. And verify that this equation has a root for theta between 1.2 and 1.3. All right, so that's the question we would want to answer. So the key part is the point furthest from the initial line. So at the point, let me just write that down. At the point of, in this case, it's the curve C, furthest from the initial line, you need to know that dy by d theta is equal to 0. So in this case, the original curve is r squared is equal to pi minus theta of arctan of pi minus theta. So we have here r squared is equal to, like they said, pi minus theta of arctan of pi minus theta. All right. And we know that y is equal to r sine theta. Okay, because you know how we would want to express this equation to be y in terms of theta. So since we know that y is r sine theta, we can make our subject to say that r is y over sine theta, okay, which would mean that therefore from our equation, which says r squared, we'll be having y squared over sine squared of theta being equal to pi minus theta of arctan of pi minus theta. All right. We're going to multiply both sides by sine squared theta. So y squared is equal to pi minus theta of arctan of pi minus theta of sine squared theta. Now we can square root both sides so that we can have y being equal to the square root, and that's the square root of pi minus theta of arctan of pi minus theta, and the square root of sine squared theta is actually sine theta, so that's of sine of theta. So this is what we have right here. Now, we'd want to find dy by the theta. Remember we said at the point of C, furthest from the initial line, dy by the theta is equal to 0. So we want to find dy by the theta here. All right. So for us to do that, we will consider, because this is a product, right? We're going to take this function, multiplying this function. So let us consider, to start with, the square root, okay? Let's just say y to be equal to the square root of pi minus theta arctan of pi minus theta. So we want to see how we can differentiate this to start with. All right. This can also be written as pi minus theta of arctan of pi minus theta all to the power of a half. All right. And I'm going to say, here we're going to use the chain rule. So let u be equal to pi minus theta of arctan of pi minus theta, which would therefore mean that y is equal to u to the power of a half. Okay, do you understand that part so far?
Yeah, I understand.
Okay, good. So we'll be having here, let's find du by the theta. Okay, we'll need this for the chain rule. Okay, so it's arctan of pi minus theta times the derivative with respect to theta of pi minus theta plus pi minus theta times the derivative with respect to theta of arctan of pi minus theta. So that's what we are doing here. So that's going to be here. We know that if we differentiate pi minus theta with respect to theta, we get minus 1. So we have minus of arctan of pi minus theta. And that's plus, on this part, differentiating arctan of pi over theta, pi minus theta. We know that, okay, well, we know that from, if you look at your MF19, if you differentiate with respect to x, arctan of x, you get 1 over 1 plus x squared. Okay, do you still recall this result?
Yes, I have the formula sheet open as well.
Okay, so it should be right, right?
Yes.
Okay, good. So that's pi minus theta. Okay, but since we are differentiating a function of theta, we are going to start by differentiating pi minus theta, which gives us -1. So we have minus, and then we will go 1 over 1 plus pi minus theta squared. So essentially we have minus of arctan of pi minus theta plus, actually minus now because of that negative. Okay, so it's minus, oh, you have to use the right pen. Okay, so minus pi minus theta over 1 plus pi minus theta squared. All right, I hope you're tracking so far.
Yes.
Okay, good. Let's also take this result, this thing here. We will also need this for the chain rules. So let's actually remove it from here and we place it down here. Right, so for the fact that y is equal to u to the power of a half, it means that dy by du will give us half of u to the half minus 1. So the minus of a half, which can be written as 1 over 2 root u. Okay. So when we do dy by d theta, we get, by the chain rule, dy by du by du by dx. I mean, by d theta rather. Dy by du is the 1 over 2 root u, and that's times du by the theta is what we got right here. All right, that's minus of arctan of pi minus theta minus pi minus theta of 1. Okay, I'll need 2 brackets on here. 1 plus pi minus theta squared to the minus 1. Okay, so we can actually write this as minus of arctan of pi minus theta minus pi minus theta of 1 plus pi minus theta squared to the power of -1. So that's going to be over 2 of the square root of u. And remember we had said u is pi minus theta of arctan minus theta. So let's place it here. That is 2 root u we now have here. So we're going to make use of this. We will need this. All right. Let's carry on. Okay. We had left it off on y is equal to this. Okay. So we want to continue with this. Okay. So we are now on another page. All right. So from here, we are going to need to find dy by the theta. Okay. And remember, dy by the theta is equal to 0 for the point on C furthest from the initial line, which is going to be sine theta times the derivative with respect to theta of the square root of pi minus theta of arctan of pi minus theta. All right. And that's going to be plus, we're doing products, remember, the square root of pi minus theta of arctan of pi minus theta of the derivative with respect to theta of sine theta. So this is essentially, for this part, this derivative, we now already have it. That's what we were doing, okay? Is this thing that we have right above, okay? So I'll just write it down, minus arctan of pi minus theta. So minus of arctan of pi minus theta, and that's so minus of pi minus theta, and that's of 1 plus pi minus theta squared to the minus 1, and that was over 2 root u. So it was 2 of the square root of pi minus theta of arctan of pi minus theta. Okay, and that's of this sine theta. So that's of sine theta, and it's plus. All right, so we need to create a bit of space here. So let me move this to the left. Okay, I think this should be fine. So that's going to be plus. Now we're on this part, and that's simply the square root, and it's the square root of pi minus theta of arctan of pi minus theta, and the derivative of sine theta is actually cos theta. So dot cos theta. All right. So this is where we are right now. Now, this derivative has to be equal to 0. So we're going to equate everything to 0. Now, I'm going to multiply all the terms by this denominator, okay? Both sides by this denominator. And if we do, we will be having minus of arctan of pi minus theta minus pi minus theta of 1 plus pi minus theta squared to the minus 1 of sine theta, and that's going to be plus. If we multiply this thing by this denominator, okay, we will be having 2 of pi minus theta of arctan of pi minus theta of cos theta, and all this is equal to 0. All right. Now, let's see what they want us to end up with. So they want us to start with this thing here. All right, so we're just going to rearrange what we have. I will start with this part, 2 of pi minus theta of arctan of pi minus theta cos theta. Okay, and that's going to be minus. So I'm going to factor out minus 1 on this thing here. And if I do, we'll be having, and maybe starting with this term, because I can see here, if we go back, after this term comes the pi minus theta part and the arctan follows. So we just want to rearrange it so that it comes out exactly as they want it to be. So I'll start with this part, which is pi minus theta over 1 plus pi minus theta squared. Sine theta is affecting everything. I'll put a square bracket here. All right. And I'll take this part. Remember, we factored out minus. So here we'll be having plus arctan of pi minus theta. And everything is being affected by the sine theta, and it's equal to 0. All right. So it looks good so far. And here there's cot. So what we're going to do is we're going to divide both sides by sine theta. Okay. So we're going to say this thing times 1 over sine theta here times 1 over sine theta. And on the right side again, times 1 over sine theta. And when we do, we'll be having 2 of pi minus theta of arctan of pi minus theta, and cos theta over sine theta is cot theta. And here they will cancel. So we have minus of pi minus theta over 1 plus pi minus theta squared. And it's going to be minus arctan of pi minus theta equal to 0. And what we have now, Amira, is the exact thing they have here. I'd want you to check to see if that's right.
Yes, it's the same.
Okay. So that's what they wanted us to show. So I'll say here, shown. On the other part of the question, they say, and verify that this equation has a root for theta between 1.2 and 1.3. All right. So we want to verify the roots. Okay, so let's do that. All right.
Just if they have opposite signs, right?
So this is where we'll be having a sign change, which means that we have to substitute. Maybe we say let f of theta be equal to this thing here, and then we will do f of 1.2 and see what we get. And we'll also do f of 1.3 and we substitute into theta, okay? And that you should make sure that you are in radians. All right. Do you want to help me with those calculations?
Yes, I think I did it. I did this part already. So
Okay, what did you get for f of 1.2?
for this, when it's 1.2,
Yes,
it's 0.151.
0.151 if we substitute 1.2 for theta.
Yes.
Okay, and for
Then
1.3?
negative 0.395.
Okay, good. So that means that there's a sign change, right?
Yes.
And that's how we prove that the root lies between 1.2 and 1.3. All right. What do you think of this question?
Long.
Indeed, it was.